So our next speaker was a gymnast for 16 years, a cheerleader in college, and has competed in Olympic-style lifting. Now, we had a lifter yesterday too, right? Who was our lifter yesterday? I forgot. Kayla. Michaela, you here? Oh, I'd like to have like a competition. We get some weights and see if they do it side by side. So please welcome today's lifter, Rachel.
Yeah, when I was thinking of what my intro would be and my fun fact, I was in my office and my friend was like, "You just have cheerleader style energy, and like you were a cheerleader, and you should do something with that." And I was like, "All right." So my 7:40 a.m. students deal with this energy. So hopefully, leading into lunch, this will be a good amount of energy to finish off the day, or the afternoon, I should say. So my name is Rachel Gidaro. I am currently teaching at West Point. Previously was at Baylor, finishing up my PhD. And my focus is time series analysis. So my talk today, unlike maybe some of the other talks, very mathematical focused, and a lot of functions you're going to see, a lot more math you're going to see, unfortunately. So for those of us that ran away from equations, I'm sorry. I'm going to do my best to just kind of introduce them and show you what I've been working on. But again, I didn't know the room. I didn't know what kind of backgrounds everyone would have. So I wanted to do a quick intro to what is time series analysis, and just give you guys all a quick synopsis of it. So time series analysis is when you have a collection of random variables indexed by time. So if you're, what I tell my students, if your X variable's time, you're probably working with time series. Time could be in years, months, weeks, days, hours, minutes, seconds, however you would want to break up your times, that you could do it with time series analysis. You'll see this in economics, with stock markets, social sciences, biology, environmental science. Again, you could see these anywhere. So it's really important to have a background of time series. One of the major differences between time series and maybe a more common model of linear regression is that there's autocorrelation. So I was even teaching linear regression yesterday to my students. And again, if we break that if they don't have independence, we have to do time series if it's related to time. So that's something that we've talked through with my class. So what are the things we're looking for when doing time series? Well, we might be interested in describing what we're seeing, and that goes beyond just mean, variance, and distribution. So I will talk through some other things you might want to look for when you're looking at your time series. Again, we'll do inference and predictive tests, and we'll show that. And then the last thing I wanted to mention that I don't really talk about in this talk, but that you might see if you look at time series data, is talking about control. And so change point time series is another area of time series analysis in which you see a pattern over time, but then something changes. COVID happens, another event happens, and now there's this discontinuity. You can see this change in your time series. Or maybe you don't know where the change happened, and you're looking at measures over time, and you think the process broke, or the tool you were using may have broken. Can we spot when that happened? So that's another area of time series. Again, don't want to talk about it today, but want to introduce that as something you might see. So again, as you're looking at time series analysis, you have many different considerations. What is your time index? How is it changing? R has this amazing package called Lubridate. If you've worked with time series data, you've probably used Lubridate to make sure your time indexes are what you want them to be. So you care about that. You also care if the process is discrete or continuous. My focus today is on discrete, but I will talk about the continuous case just a little bit. And then do you care if it's univariate or multivariate? There's a really cool time series looking at foxes and rabbit populations and how those, again, you'll see the pattern, and it's very cool. But again, I'll start with just the univariate case today. So as we look at time series plots, again, it goes past just looking at the mean, the variance, the distribution. We also care about the trend and how these things are changing over time. So the mean isn't necessarily constant, it changes. The variability isn't necessarily constant, it might change, and how do we model that? We also care about how smooth it is, and do these stay, do they stay consistent over a domain, or do they change? So one of my favorite time series to show people is airline passengers data, because you can see all of this at once, right? You can see that the mean is changing over time. You can see that the variability is changing over time. And you can see this seasonal pattern that you wouldn't see in normal linear regression, right? We can see that maybe every December, these increase, right? We see that like more people are traveling and the passengers are increasing. And so there's a seasonal component as well. And so time series can kind of tackle all of that, where maybe other models or things we've looked at previously don't. So, oh, there we go. Okay, so the first equations I'm going to show you are as it relates to the Gaussian autoregressive process. And for some reason, that slide does not want to show. So there is a more formal definition of the Gaussian process. I'm not sure something's wrong with that slide, but that's okay, because what we care about is this mean, variance, and how we model that. We'll talk through exactly how I was able to do case up ahead for prediction using this model, and you have this mean, you have this variance, and using that, you're able to, again, forecast into the future. And so that's the Gaussian autoregressive process. That's the process that is for continuous variables. We don't only care about continuous variables. We care about discrete variables. What if, again, we're observing counts, and very small counts at that. We're only observing 1 to 2, 3, 4, 5 people coming in at a time, and we're trying to measure that. Early papers looked at the discrete autoregressive moving average process, the Dharma. This discrete process, while almost too simplistic in nature. So this one didn't really get at it. And Markov chains, if you've heard of those, are almost too complex, and they would be very hard to model most of your time series. So those were the original models that were out there, and then comes in the integer autoregressive process, which is what I'm going to talk about today. So with the integer autoregressive process, the way it worked is it was very similar to our Gaussian autoregressive process, except now we have this binomial thinning operator. This binomial thinning operator allowed us to treat it as discrete. So you have your x variables that are now either geometric distribution, Poisson distributions, any type of discrete distribution you would be interested in. And you put this alpha thinning, which is a Bernoulli process, on top of it, and it allows you to make it a discrete process. Okay. I'll also be talking about other approaches today, the Poisson-Linley distribution and the zero-inflated Poisson distribution, and how we kind of looked at those for prediction. So with forecasting discrete processes, one of the reasons that this is a really important area within time series analysis is because you want coherent forecasts, so forecasts that don't violate known constraints. Again, if you are doing counts, you should not be using continuous processes because it's going to give you a continuous answer, versus discrete will give you a probability associated with observing a 0, a 1, a 2, a 3, whatever you would need. So this is where Gaussians are not coherent, and we would not want to use those forecasting techniques. We will still use conditional expectations, which will give you an average, which will give you a non-coherent forecast, and we'll look at how that compares as well. You'll see too, one of the things that I stressed in my research, and one of the things I looked at, we looked at many different measures. We looked at mean square error, we looked at mean absolute deviation, and we looked at percent true prediction. And oftentimes the conditional mean square error will be lowest when looking at the conditional mean, but that's not the only thing you'd care to look at. And so we'll talk through that as well as we get into later in the talk. Okay, so here is the first process I looked at. This is the geometric integer autoregressive process. Again, very similar to the regular AR1 process that many of us may know, except now X is geometric, and our errors are a process of Bernoulli and geometric. And this was written from McKinsey's 1986 paper. Some of my slides are just not showing up. I'm not sure why. Hold on. Okay. We're going to do that so that way we can see it. Okay. Our error distribution looks like this. And again, now we have a mean and a variance. And because the x's are geometric, those are the same mean and variance geometric that we would know. Now, the thing that's different here is we're actually looking at failures as theta. Theta, our parameter, is going to be in rates of failure, not rates of success. The reason this is important is because we want to be able to observe 0 counts. So not just 1, 2, 3, 4, but also 0. And so to do that, we need to have the count of failure. So we have to have it as a failure rate, not a success rate, or when the first success happens, that was the geometric distribution. Okay, and when we look at the case-step ahead conditional distribution, or yes, the case-step ahead conditional distribution, this is what that looks like as far as, again, how I'm modeling this. Okay, I'm just showing these equations to give you some context for what I did. It's not necessarily important that we fully understand everything that's happening here. Okay. And again, the modeling the expected values, the variance, you can be done this way and allows us to better evaluate how well our model's doing. Okay, one of the reasons the geometric is not again, no statistician in here, no data scientist in here only picks one model and says, I'm done, right? Nobody's like, oh, I got geometric. Let's just use that and call it good. Like, I'm done. This is awesome. We had to look at other models. There are other models out there that we may care to look at. So one of the ones I wanted to look at was the Poisson-Linley distribution. This allowed for more variability. First introduced in 2018. One downside was this, is that it gets really complex really fast. So I kind of showed you the geometric formulations. We're about to see some really gross ones. They're going to get grosser. That's what I tell my students. Sometimes it just gets more complex and it gets gross, but that's okay. It's really good stuff. So yeah, so even the error distribution, this is just the errors. That equation there, that's just the errors. So even modeling the errors are now way more complex for the Poisson-Linley, but again, it allows us to have more variability. And here is our case-step ahead conditional distribution that we need to use in order to forecast into the future. Again, you can look at the papers if you're interested in like really how this came about, but this is the formulation I'm going to use to then forecast forward. Okay, and then again, we have our means and our variance. That will come into play as we look at, again, prediction. The last distribution I want to introduce that I looked into was the zero-inflated Poisson. So a lot of times in count time series and discrete time series, we have a lot of zeros, okay? Well, maybe Poisson-Lindley, again, adding more variability might be a benefit, but we might also want something that accounts for all the zeros we're observing. So we have the zero-inflated Poisson. Zero-inflated Poisson, again, Poisson rate, but then we also have our, we also have pi as our between 0 and 1 variable. It allows for that Bernoulli process. Okay, so we have our zero-inflated Poisson with our y distribution being the Poisson, the z being the Bernoulli process, and then we still have our alpha thinning. So now we have 3 parameters where we previously only had 2 for the geometric and the Poisson-Lindley. So that was something we also had to take into account. Okay, and then that's that beautiful formulation. Again, long formulas, but again, allows us to do those predictions. And there's the expected value and variance as well, again, for prediction. So one of the reasons I was really interested in this is that originally when I was doing my research, if you've ever taken a time series analysis course, you probably didn't learn anything about discrete time series. I know I loved my time series course, but we didn't even touch them or talk about them. We just stayed with autoregressive process and kind of hung in there. But there was actually a little bit of contradictory information about using the Gaussian versus using discrete processes and which one's better and when is it better. And so it was like, okay, there's contradictions out there. Maybe we can get a more formal understanding of what's happening and when we should use Gaussian and when we can use these discrete processes, or when we should, right? So that was part of my interest and part of why I got started in this research. Okay, so part of the estimation process, part of our research, again, we were doing comparison, but we also did estimation of the parameters. And the zero-inflated Poisson did have a paper where they'd estimate the parameters, but something that was not investigated was the variety of differences you could see. So we could use conditional least squares as one of our estimation procedures, Yule-Walker, or maximum likelihood estimation. Again, depending on your time or your statistics background, you may have heard of those before. They're just all 3 different techniques to estimate our alpha, our lambda, and our pi. Okay, so we're going to compare these. So quickly, here's again those formulations. That's the conditional least squares and how you'd formulate it. It does have a closed form expression, which makes it very nice and easy to use. Same with the Yule-Walker. It also has a closed form expression. Again, you can get some estimates for alpha hat, pi hat, and lambda hat. In some cases, again, I think as n goes to infinity, these do become the same estimator. So conditionally squares and Yule-Walker can become similar. The last one we look at is maximum likelihood. This does not have a closed form and does need to be optimized. And so you have to use an optimization algorithm to do. So this one does take longer and is a little harder to code. So our simulation design, again, we wanted to investigate how well to estimate these parameters because that then affects our prediction. We have these formulas, but we have parameters. We got to estimate to make the prediction. So we replicated 500 zero-inflated Poisson integer-autoregressive processes. We checked it at various alphas, pi's, and lambdas to see how this would affect it. We then compared and computed the averages and standard errors for these. One of the things we had to keep in mind is that with conditional least squares and Yule-Walker, you can have values that don't make sense. So alpha needed to be between 0 and 1, pi needed to be between 0 and 1. Lambda could be anything. So thankfully, that one was good. Or anything above 1, which we didn't have any problems with, or anything above 0. So we had to look at, are these not actually feasible sometimes? And the truth was, they weren't always. And so we did start with just a comparison of, with a time series length of 100. Alpha is set to be 0.2, and it's being estimated to be 0.28. But it's a pretty big difference in time series that would really affect your forecasting. For Yule-Walker, it's 0.37, which is even worse. And then our maximum likelihood estimator actually does perform fairly well. And so there is some natural variation in that. And our standard errors do increase or decrease as the series length increases. So if you have a really long time series, these maybe aren't considerations you care about. But if you have a short time series, which was what we looked at in particular, you're going to have a lot of problems when you look at these. So again, estimation, we're already seeing maximum likelihood estimators are better. And then when we look at the percent that are actually admissible, they shouldn't be considered because alpha is being underestimated or overestimated past what it could even possibly be, then you have to throw out even more options. So that is really something we investigated again, was looking at conditional least squares in Yule-Walker versus maximum likelihood. Really should only look at maximum likelihood estimation, but we are curious still to see how they would actually perform if they can estimate well. So that was one example where they did really bad. But again, that's just one case. That's when alpha and pi are 0.2 and lambda is set to be 1, 2, or 3. What about other cases? Is this just a common problem? If we change the alpha to be 0.8 and we change pi to be 0.4, again, as series length increases, we see that it does indeed improve in its accuracy and our standard error does decrease. We also see that there are less inadmissible values. So it does matter not only the series length, but what your parameter values are as far as how bad these methods are performing. So that's one thing we look at. And so again, still interested in seeing how they would actually perform on a real data set. So one of the data sets we investigated was sex offenses data set. It had 144 counts of reports from Pittsburgh, monthly data. A lot of zeros here, right? A lot of zeros, 1, 2, 3, low values. So using an autoregressive process should not perform well. So we, again, compared not only the Poisson-Linley, geometric, zero-inflated Poisson, but also looked at how the Gaussian would work as far as this data was concerned. Again, just to kind of show you more about the data, a lot of zeros. Highest value observed was 6, variance, mean 0.59, and that just gives you an idea of the data. Again, depending on your background in time series, you look at the time series plot. Looking at the ACF and PACF plot, we know we're doing an autoregressive order 1, meaning we're only looking at one step ahead, one step back to predict forward. This data set is over-dispersed using an index of dispersion. Again, 62.5% of the data are zeros. Here's that kind of just showing you that we did do our checks. We did make sure this was an autoregressive order 1 process. So here are the estimations we got for the zero-inflated Poisson for the sex offenses data. We saw that conditional least squares would say alpha should be 0.4. Yule-Walker said 0.8, which is very different. And then NL said 0.2. So again, across the board, not estimating maybe well, we don't know, right? We don't know the truth with this data set. So we're looking and we're seeing very big differences as far as alpha is concerned. Less so with pi and lambda, but still, again, we're interested to see how they perform. So here is the conditional case step ahead predictions. And these are probabilities. So given one step ahead, it's saying probability of observing a 0 should be about 0.625. So you'd say we predict a 0, so on and so forth. And you can see, again, even though these predictions were very different and these parameter estimates were very different, the thing that shocked me was how our conclusions really wouldn't change. So our conclusion wouldn't change. We would still predict zeros for all of the methods, the next value to be a 0 for all the methods. Again, they are different, but not different enough for our conclusions. And then just to show you also for the Poisson, even though these were not our focus, also we did do Poisson-Linley. Again, less variation from conditionally squared to Yule-Walker, and even MLE, again, 0.7, 0.6. And then we had the geometric as well. Again, we're seeing 0.7, 0.6 for the probability of 0. Okay, so now we had to assess these forecasting measures. So we trained our data set as we do. We trained it on 80%, we tested on 20%, because we know the truth for what values actually occurred. And we see how well we did. So we looked at mean square error, mean absolute deviation, and percentage true prediction for both the median and the mode. Okay, and those are those formulations. Again, you can look at the literature and find how we calculate root mean square error, mean absolute deviation, and percent true prediction. So what I found more fascinating was what actually happened, and as far as, again, the literature disagreed on how well these models do versus Gaussian. And if you look at PRMSE and PMAD, you'd say, I mean, almost all the same, regardless of distribution, which is fascinating. But where the big difference becomes, typically in this true prediction percentage, Gaussian is doing worse. And now the sex offenses data was just one example we looked at. I do have another table in here where we looked at skin lesions, and it was a whole 20% different on percent true prediction. And so I went back to the literature I looked at, and the ones that said Gaussian's about the same, we're looking at mean square error and mean absolute deviation rather than percent true prediction. So again, if you want to have a full understanding of this, you really should be thinking, again, what's your focus? It depends on the problem. Do you care more about being accurate every time, or do you care about just overall reducing that error? And I think being accurate, especially in discrete time series, is maybe of more value. So these percent true predictions are really what you should be looking at. Okay, and then this was the skin lesion. So I did say we had another data set. This is not the sex offenses data set. We had another data set we looked at called skin lesions. It was counts of skin lesions. And zero-inflated Poisson, because of 3 parameters and because of this very short time series, it actually wasn't able to estimate for conditional least squares. It gave us an alpha above 1, and we weren't able to run that model. And so we couldn't even use that model in that case. But we do see, again, that both the discrete processes work better than our traditional. And again, as far as the discrete processes, there weren't very many differences, at least for this data set, as well as the sex offenses data set. So I threw a lot at you, and I do apologize. I am fast talker. My students tell me that. Again, it's that energy. It's a high energy person. But my point here is there was a lot I did, and I'm trying to throw it into an R package. So I do hope to get that R package out. There's currently no R package for discrete time series to run these models that I had to run. So I had to type up all those fun formulas that I skipped through, which was really good. I love misspelling alpha like 5 times. Really helps my coding abilities. So my big next step is to get this into an R package that's easy for users. You need to have more options out there than just the Gaussian, which has awesome R packages for the Gaussian. Running an auto.arima function, easy peasy lemon squeezy. Coding these discrete time series, less so. So if I can make a good product, that would be my next goal. And then to look into seasonal and continue to add to this package so that you have more and more options as far as running models and seeing how well they're performing. And so that's kind of just where I'm at and what I'm looking to do. But thank you so much for having me. And there are my references and any questions, but thank you.